All right, today we're gonna go through Nearpod today, like I promised you, because this last section or two that we're doing, I'm mixing them together. There's a ton of theorems, but I don't really have you memorize the theorem. What we're gonna really focus on is the formula that it talks about, and it's not really introducing anything crazy new. It's really not. It's talking about secants and tangents. That's what we're covering. Very easy concepts. The problem is we got to know how to use them correctly. And so that's what we're going to look at today. We may not get to all this today. It's totally fine. It's whatever we get to, we get to. It's fine. So we're going to go through the Nearpod. So if you want to get logged in there, that's great. But before we do that, I do want to talk about the 5-minute check we did yesterday. Because I want to see, kind of where we're sitting, how you felt, if you got the right answer. So we're going to do that first. We'll take maybe a minute or two, go through those answers one more time. I'll even hand back your little card so you can see how you did compared to it, because I want to look them over just a little bit, see kind of where we're at. It came down to like the vocab was the one that really got people. They just didn't understand, I think, the question. So, but everything else was usually fine, as long as you had the numbers in the right spot. The most common mistake on like the work involved was question number 1, putting the numbers in the wrong spots in the Pythagorean theorem. Like overall, in all my geometry classes, that was the number 1 question. So that's kind of our goal today. It's kind of a tall order. We got a lot of stuff to go through. I thought the Nearpod would be kind of the easiest way to display the data to you today, so we'll use that. We got some, we might try some different things for next week when we start doing the review and stuff, or maybe even tomorrow if we get to the review. I don't know where we'll get. But homework is due tomorrow. Keep that in mind. Due Friday. That's the assignment that I gave it on the board yesterday. So if you were not paying attention when you did have homework yesterday, that was your page 736. It was based on tangents. So hopefully you kind of figured out how that works and you can kind of piece that stuff together. But before we get to that, I do want to hand out some stuff here. So I'm going to hand you guys practice guides for chapter 10. I know that we probably won't start reviewing until maybe tomorrow or Monday, at the latest. But I do want to make sure that everyone in the room at least gets a copy of the practice guide. Now I don't have them stapled, apologies. Maybe that'll make it easier. So didn't have time this morning to actually staple it, but when you turn them in, you'll staple them together. Now remember, I always try to give the same instructions on these practice guides. Make sure that you are, here I'll just walk around here. Make sure on these practice guides that you are completing them, right? We work through them in class. I'll give each of you just the first page. And here's the second page. So this is what the test will look like. It'll look identical to this. That is basically what it is. It's when the book and pick a different picture or a different number. So the code?
VFR.
Yeah. Did you guys hit the second page yet? Okay. I'll give you another one. There you go. Okay, here's the second page. I think there's 3. Double check that. Is there 3 there?
So, you're gonna bomb this one too.
Oh, this is.
Okay. Okay, did everyone get a practice guide?
That's it?
Okay, again, if you want a stapler, I can hand that around. If you guys want to do that, you can staple them.
Oh.
So, if you don't, that's fine, but I want them stapled when you turn those in. This is what your test's going to look like. Right now, tentatively, I have the test set for Tuesday next week, but we still have to start reviewing it. We're not there yet, so I at least want to get it in your hands. This will be your last test, so, and then after you're done with that one, you just work on that practice semester test the whole time. Does that make sense?
Yeah.
So, pretty easy, so, all right. But yeah, pretty straightforward. What is it, 13 questions? I think it's pretty easy. The vocab is significantly shorter than previous tests. We just didn't have a lot of vocab words in this test, or in this chapter, this section. Just because, there's tangents, secants, circles, and so the parts about a circle is like radius, diameter, circumference, area. But that's pretty much about it. Then after that, it's just, the basic stuff, formulas, how to work with Pythagorean theorem and all that. Okay, next thing I want to hand out. Your 5-minute check. 5-minute check part. Okay. Let's see. Hand these out. I want just keep these out in front of you. We'll go through this question here. The 3 questions we had, I'm gonna go through these pretty quick. You can see how you did. This is just, I want to look these over, because again, I said that these were not graded. I just wanted to check where you sat. There were some classes I told them it was a graded quiz, and they were all stressed out about it. It was pretty funny to watch that. So, I had a pretty good chuckle about it until they found out it wasn't graded. Mitch, Nelson, Frank, Kieran, Nelson, and Luke. Nice. Okay, everyone get one? That was here anyway? Okay, let's go through those questions first, because those are pretty straightforward, pretty easy. Let me throw it up on the board. Here we go. Oh, perfect, okay. So, first question, it was to find BU. I had that corrected after you guys left. It said, I think yesterday it said like BU, that was stupid, but whatever, BU. So to find this is your right triangle, because the right angle meets the radius in the tangent. So this is your A, this is B, and this is C. Because the C has to be the one wall that doesn't touch 90. That was the number 1 question people got wrong. So it was x squared plus 15 squared equals 24 squared. The number 1 question people got wrong, they put the 15 and the 24 in the wrong spots. Some people add them together as opposed to having them on the opposite sides of the equal sign. How I know where they go, the hypotenuse, the one that's labeled with C, has to be by itself. And how I know that it doesn't touch 90. So this is x squared plus 225. 225 equals, what is that, 576. You subtract this over, and we get x squared equals, let's see.
351.
What is it?
351.
351. And if you take the square root of that, square root of 351, just below 20, what is that in?
18.73.
27, there you go. Oh. Okay. But the number 1 thing I was trying to look for, did you even have it set up right? Did you have the numbers in the right spots? Did you subtract it across? Did you take the square root? That's what I was looking for. Some people went further, they wrote the decimal, which I wanted 1 or 2 decimal places. But I was trying to check, did you even set it up right? Did you even know which parts go where? Okay, questions about number 1. There was a couple people that didn't even attempt it in those later sections. They just said, don't know. I wouldn't do that. All right, second question. Now this one is more open-ended. You just had to draw 2 circles that are somehow externally tangent. This is an external tangent. It's when 2 circles meet on the outsides. Okay, they're not inside of each other, they're outsides. That's to be externally tangent. Now, here's the vague thing. It said, I wanted a tangent line to both. There was 2 different lines you could have drawn. 2 different lines that could be tangent to both circles. Number 1, you could draw this line. Raise your hand if you had that line. Yep. That was the one I probably had in the notes. So if you were using your notes, you probably had that drawing. Does anyone know what type of tangent that is? It's internal. It is a common tangent. Don't get me wrong. It is a common tangent. But it's internal. This is an internal tangent. Now why?
That's crossing the line between 2 circles.
Yeah. Why it's called internal is absolutely right. If you have the line that connects the 2 centers of your circles, it crosses that. It goes through the inside of it. Okay? Now, that was one way people had it drawn. Some people didn't. As you could tell, there were some people that didn't have that. So you have your 2 circles. Oh, that was a terrible 2 circles. The other common drawing, the other common tangent, was this one. Raise your hand if you had that. It could be top or bottom. Okay. Okay, that is called what type of tangent? External. Okay. This is an external tangent. That's what I wanted you to describe your tangent lines. I know that was kind of a confusing sentence, like statement question. The classification of it is either internal or external. Now don't get me wrong, I think it was Hanson, you said it was a common tangent. That is the correct term. But the specific type is called external or internal. Got it? So that was kind of an open-ended question. I want to see kind of what you were drawing there. All right, and the last problem. Okay, the last problem where you had to find the perimeter of your object here, the perimeter of your triangle. Okay, just remember that when you have these exterior points on the outsides of the circles, these tangent lines that go towards the circle have to be the same size. So this 13 can hop to here. So this stick is 13, that one's 13. If this one's 8, this one over here is 8, then these two have to be equal to each other. Because they're the same tangent line, because they're coming from the same exterior point. So 5x minus 10 has to be equal to the 2x minus 1. Subtract this across, add the 10 across, so this is 5x minus 2x. Negative 1 plus the 10, which is 9. This is 3x, so your x is 3. And what do we have to do with it?
Add all the sides.
Yeah, you had to add all the sides, but you had to plug that one back in. Because if you didn't plug that in, how do you know what sides to add up? So if you plug this in, 2 times 3 minus 1, this turns out to be 6 minus 1, which is 5. So this is 5 and 5. Then you can add it up. 13 plus 18 plus 21. And then you can figure out what that adds up to be. Okay, 52. Okay, questions, comments about any of the parts? Okay, see how you did? Now, the reason why I gave you this, I want to kind of see where you're at. Number 2, if you had these on your test, because obviously you're looking at your practice guide today, could you do them successfully and set them up? Because these are things like we have to know how to do them. We have to know how to set them up. All right, we're good though? Perfect. Moving on. Okay, you can keep those little cards, those are yours. All right. Okay, let's get to our near pod today. Okay. Get the lights so we'll get started. All right, so goals today, as you can see on the board up here, plus on my little PowerPoint. Let's plug this in so I can actually change the slides. Okay, goals today. I want to go through the definition of a secant and tangent real quick, just to compare them. I want to talk about theorems 10, 12 to get to 10, 17. Now we may not get to all of them today. It's fine. I said, wherever we get to today, we'll just continue tomorrow. And then at some point tomorrow, we'll probably start reviewing. We'll probably do more hands-on stuff with this tomorrow where I have you in little groups and we try out a couple problems. I may not give you an assignment over this stuff because it's not difficult. I considered the last stuff we did, this assignment, page 736, to be kind of challenging, right? You had to do Pythagorean theorem. But the stuff we're doing today, it's not doing it. It's simple algebra 1 that I'm pretty sure a 5th grader could figure out. But so that's why I say these formulas are super easy. There's no hard, difficult type of math. Maybe the last theorem in general will be the tough one, but it's really simple. When you see it, it's pretty easy. So homework today. This is the stuff I gave you yesterday. It's due tomorrow. That's the page 736. I have it on the board over here. Make sure you're kind of working on that. If you already have it done, fine, dandy. I think grades I'll be updating tonight for you guys, probably after school actually, since we have a little bit of time before soccer starts. But that's due tomorrow, and that'll be in for the weekend. All right, so we're good so far? Okay, let's go to the next slide here. Okay, I want to talk about secants. So, is the near pod actually working for everyone? Just trying. Okay, just making sure. Okay. All right, so on this one, this is a secant, right? This is the definition of a secant where it's a line that intersects a circle exactly twice, a line, so it keeps going. That's why there's arrows. So in this picture, I have 2 different secants. They're different than tangents. What was the main difference between a secant line and a tangent line? Only hits the circle once. So secants hit twice. So a good example of a tangent would be something like this, where it hits perfectly once. Now it doesn't have to intersect the actual secants. You can have tangents line wherever you want. That's what we did in this previous section. That was the section 10.5, tangent lines. but secants pass right through the object. Well, there's a bunch of different interactions when you start doing this. When you start drawing secants and they start crossing like this, if I have two of them and I start moving them so they actually touch each other, you have a bunch of different outcomes that can happen on a circle, because we've actually discussed from like section 10.4 and stuff, that the chords of a circle, this is a chord, like the inside of the circle where the secant inside, just this little chunk right here, those chords have very specific lengths. Or the arcs have specific measures, like the angles of these arcs that's left over. Okay, and that's what we're looking at today. Like how, when you draw secants or you draw tangents or you draw chords, what happens to the arcs? What happens to those segment lines? Okay, that's what we're looking at. Now remember, when you draw a secant, there is a chord inside the circle. Chords are just that little stick. It's starting and stopping point in the circle. That's where all this stuff is going to come from. Okay, any questions with the definition of secant? That word is fair game for the test, so be careful of that. Especially chord. Okay. Alright, moving on. Okay, 10-12 today. Now it's probably showing up in your Nearpod. I have everything there. I have the picture, I have all the formulas, but they're going to pop up here one at a time. Okay, if you were to draw two secants, or two chords, if you will, so you can shorten them up, make them chords, and they intersect in the middle of a circle, somewhere. It doesn't have to even hit the center. They somehow cross inside of a picture, like this. Right? These are two secants, they cross. It's not even the center. You can tell it's not the center on that picture. Then what this theorem says is that the angles formed in the middle here, like where these things actually cross, you can actually find them. So like this picture has angle 1 and 2, and how they're related is that angle 1 is actually related to the arc that it looks at. Well, the problem is angle 1 is actually looking at two different arcs. They try to color code to make it all pretty like. So angle number 1 is actually looking at that arc, agreed? Well, it's also looking at, this is angle number 1 again, because you can go vertical, straight across the line. It's also looking at that arc. So this first theorem talks about there's an actual relationship that you can actually find the numbers for both of those. Okay? And so here's the formula. So to find angle number 1, if you had the two arcs that angle number 1 is looking at, you can actually find the measure of angle 1. So somebody just make up an arc for AB. Make up any number you like.
11.
What?
11.
11. Okay, we're going to make up, this is 11 degrees. Okay? Somebody make up a different number.
24.
24. Okay, 24. So these are my two arcs. That's the arc on the top, that's A to B. This is arc C to D is 24, so they're minor arcs. Well, what this theorem says is that you can add the two arcs together. So 11 and 24, you actually add them together. And then you cut that answer in half. You half it. And that will give you angle number 1 in the middle of the picture. And it's not even the center of the picture, it's just somewhere in the middle of the circle somewhere. Okay, so if we add these together, what is that, 35? Then you cut that in half. So what is 35? Is that 17 and a half? Something like that. 17.5 degrees. And that's your angle, that's the measure of angle number 1. You can add the two arcs. Now, most people look and go, Ward, how is that even possible? Like, how did number 1 even work that way? Like you look at, I understand it's looking at two different arcs, but why do you add them together and cut it in half? Like where does that come from? Well, it's based on the stuff we did back in section 10.4 and 10.3, where you had inscribed angles. Angles across the picture that they're half the arc that they look at. Now, angle number 1 is not across the picture, but there's a way to explain how angle number 1 works and why it's always half. So this is literally how they prove it. This is the way that they show it in college. They draw a line connecting B to C. So they draw this segment right here. So it makes this triangle. So does everyone see that? It's making that triangle, okay? Angle number 1 is outside the triangle, agreed? It's what they call an exterior angle. It's outside the triangle. Well, what we talked about in this class, it was back in chapter 4 and chapter 8, is that if you had an exterior angle of a triangle, that's equal to these two angles added together, whatever they are. Because an angle on the outside of a triangle is always equal to the two on the inside that are called remote interior. Angles that are far away from it, but they're inside the picture, the remote interior. Well, if you look at this, angle B is across the picture and it's looking at that arc. So what we talked about in section 10.3 and 10.4 in this chapter is that when an angle is across the picture, it's half the arc that it looks at. So it's half of 24. Okay, that's angle B. And angle C, let me get rid of all these arrows, angle C is across the picture and it's looking at that arc, which is half of the 11. Because again, when an angle is actually across the circle and it's touching the circle, it's always half the arc it looks at. That was this couple sections ago. Well, when you add these two together, that makes the angle on the outside. That makes the exterior angle of a triangle. Well, I can factor out the half, because they both have half in common. And that's where this formula comes from. That you can actually pull out the half because each of them have halves on them. And that's the formula, and that would be your angle number one, the angle on the outside of the triangle. So what you're actually seeing there is actually the definitive proof of why it works, and it's using remote interior, and it's using inscribed angles, angles on the inside of circles. So kind of a cool concept. Now, what I said is this is easy, because it is. If you want to find angle number one, you add the two arcs it looks at and cut them in half. If you want to find angle number two, you look at whatever these arcs are, you add them together, cut it in half, and that's angle number two. And again, that doesn't even have to be the center. The center of the circle is like here, it's not even close. So, okay, are we good with the first theorem?
So would 17.5 go down like below the 1, 2? Or
Yeah, so yeah, the 17.5 is here, and then it's also here. So it's in both spots because it's vertical to each other. Okay, are we good with the first one? Okay. Now, the rest of these theorems, like 10, 13, 10, 14, they're all kind of based on this style. They're all based on the same type of problem. In fact, the next theorem we actually look at, which is 1013, takes us back and discusses why this one worked in the first place. It discusses like why you actually have half angles and all that good stuff. So it takes us back to what section 10.3, section we did a couple of weeks, or actually about a week ago from today. Okay, we're good though? All right. On this next part of your the next part of the Nearpod, I'm going to have you plug in your own numbers and try this theorem out. I'm going to leave this on the board, and I want you to plug your own numbers on the picture and actually find angle number one. Okay? So here we go. So on your picture, so I'm going to leave this up here. I want you to make up your own numbers. Don't use the 11 and 24 like I used. But make up your own numbers for the arcs and find angle number one. And then I'm going to tell you how you can find angle number two. So draw in there, make your own numbers you can use. So if you look at the instructions, it says make up your own numbers, find the measure of angle number one using your own numbers you made up. Once somebody has submitted one that I kind of like, I'm going to share it with everybody, and we're going to talk about why I like it. Really, the goal is to just get through these angle ones, and then we'll be done today. So again, I want you to make up your own numbers for the picture and try to find angle number one. And again, the numbers you're making up, you better make up the numbers and put them here and here. Because that's what I just explained. Use the arcs that angle one is actually looking at. give everyone maybe another minute. I already have one picked out that I like, so. Unless I see another one that kind of blows my mind, the way that you did it. Two people have the exact same numbers and they're not even sitting remotely close to each other, which is crazy. Okay, will it hurt anyone's feelings if I share one right now before you're done? Okay, perfect. So I'm going to share one. Two people actually had the exact same numbers, which was like, did not expect it. Okay. All right, is it showing up on your screen? Okay. So the numbers I had, and the two people had these numbers, it was a 10 and a 20. Okay, so they didn't use my numbers, they didn't use 11 and 24, so we're good. You add the two numbers together, so 10 plus 20, you add them together, you cut it in half, so this is 30, you cut it in half, and you get 15. That is your measure of angle number 1. Now, why I like this one. This one, the example that they picked, these multiple people, this is the best type of numbers to actually show what's going on here. That this is my easiest way to explain it to somebody. That no matter what the arcs are, and it doesn't matter where these lines cross, this number that's in the middle will literally be the number in between them.
What's the mid something?
Yeah, it's almost like a mid-segment kind of a thing for like trapezoids. It's the exact same thing. I love the numbers they picked because it perfectly shows that angle number 1 will always be the number perfectly in between the two arcs that you picked. Does that make sense now? It's the middle number right in between. So it's kind of like the mid-segment from trapezoids. Now, how can I find angle number 2? Now that I know this is 15, how do I find angle number 2?
To do the same thing, the one it's looking at.
Yeah, you could do the ones it's looking at, or, common sense, what do these two have to add it to be? 180, it's a straight line, right? Straight line. So if that's 15, then this would have to be a 165. So that adds up to be 180, not on a scale obviously. But it has to be a 165, so it adds with the 15 to make 180 degrees, because that is a straight line. Straight lines make 180. And then that way you kind of know that these angles will have to be kind of big. Because they have to average. The middle number has to be 165. So we can even make up numbers. If you knew that that was a 165 sitting there, I could just make up numbers. This could be a 160, and this could be 170. Like they could be just stupid numbers. 165 is in the middle, right? It's the perfect number in between. I wouldn't do that, but I mean, that's technically what you could do. Okay, all right, are we comfortable with that first one? Like once you see the shortcut, it's kind of hard to unsee it. It's like, okay, it's the number in the middle, got it. Even though it's in the center. All right, moving on. But very good. Okay, next, 1013. So I only have a couple theorems. We might be done after this, not this one, but 1013. Okay? All right, so this one talks about, and this explains why the last ones kind of work, that when you have a secant tangent, so you have a secant line, you have a tangent line, and they're looking at arcs, right? These are called inscribed angles again, angles across the picture. They could be tangent lines, they could be normal chords that do this, but they're always half of the arc that it looks at. So this is just one of those explanations that this angle is looking at that arc, right? It's got to be half of it. So this theorem is a theorem that was really close to one that we did back in section 10.3 and 10.4, right? The inscribed angle stuff. That if you had this arc, so somebody give me just a random easy number to work with.
106.
106, okay, 106 degrees. Then angle number 1 has to be half of it, because that angle's inscribed. It's literally on the circle, looking at the arc, so you still cut it in half. So angle number 1, the measure of angle number 1 would have to be what? 53 to make 106, like that's half of it. And that's the formula that you're probably seeing on your little near pod that's showing that it's half the arc. Bless you. And it works for larger angles as well. But this theorem and the ones we had back in chapter 3 kind of helped explain why theorem 1012 worked. That angles across pictures. So, you know, like what we did is we did problems like this a lot in that third section where you had, you know, this arc is 20, then the angle across from it was 10. But we can make it bigger, right? You can go bigger than that. This explains you can use secants and tangents to also do it. But it's still half the arc that it looks at. So if I had a really big arc, I could cut it in half still. All right, questions, comments about 1013? This just helps explain why the last one worked. I just want to review that stuff with you. Okay, I don't think I have a near pod example of this one. We're just going to move on to the last one today, last theorem. Okay, we're good though? Flipping to the next one. Hopefully no one has a problem with that. Okay, 1014. Okay, last one today. This is the absolute last slide today. 1014. You can draw tangents, secants, multiple of them, and they can have different outcomes, but they don't have to cross on the inside, right? If you have secants or tangents or whatever combination you have, they could cross on the outside of a picture, like this. These are two secants that cross on the outside. Now they're also called secant segments, which I know is kind of weird, that you can have a secant, but you can have parts of it, which are called secant segments, or even in the middle is a chord that's part of a secant segment. So yeah, the secants that cross on the outside, they could be, and we'll get to the formula here in a minute, they could be, like one could be a tangent line and a secant, they cross on the outside, or it could be just two tangents that cross on the outside. But what this theorem is trying to explain is that you can find the angles at those spots where they meet. So today was all about angles, tomorrow will be all about segments. So the goal here on this one is I want to find this angle A, right here, this angle. At angle A. And we can do it for any of the pictures, they all have the same formula by the way. Any outcome. That this angle, since it's looking at these two arcs, like it's like a periscope, right? You look through a periscope, you have a lens in the front, lens in the back. The two lenses on the periscope directly impact what you see at your eye, the angle at your eye, okay? So these two, what you do is you subtract the two arcs from each other, and then you cut the angle in half. So, somebody make up two numbers, please.
37.
37 and, what was the other?
13.
13? Okay, 37 and 13. Let's say those are my two arcs. You know, that's the measures of them. All right, 37 degrees and 13 degrees. What you do is you subtract them. So you take the big number and you subtract the smaller one. That's just how it always works, big minus small. And then whatever you get, you cut that in half, and that'll give you your angle A. So the measure of angle A is half, what is that, 24? And you actually subtract that, which is what, 12 degrees? And that's the measure of angle A. That's what they're saying. So the angle at A is half the other two subtracted from each other. And again, the reason why this whole thing works, it is based on triangles again, exterior angles of triangles, and rearranging it. So it's based on exterior angles of triangles, or you could draw arcs in there and have exterior angles. Okay, questions at all? Okay, we'll probably, tomorrow what we'll do is we'll pick up with this one right away. We might do like on tomorrow we might do like on the near pod, I might have you try one. I'll review this one with you one more time. Then I'll have you try where you plug in some of your own numbers, and I'll just pick one of these three pictures and we plug them in. We talk about how you can find it. Maybe I'll even do the proof tomorrow, but the goal today was to get through these notes, talk about all the angle formulas, And then tomorrow we'll talk about segments. Because obviously we haven't talked about the lengths of these arcs and, or the lengths of the actual like secants and tangents. Those directly impact these things too. But very, very easy formulas. Just remember, they cross on the outside, you subtract. They cross on the inside, you add them, and you find the average. Okay, that's it. Very easy. Don't lose that practice guide. Hold on to that. We're going to start redoing possibly as early as tomorrow. Might be the second half tomorrow.